Hello, everybody, and welcome to the virtual seminar series on Gaussian processes, spatial-temporal modeling, and decision-making systems. Thank you so much for joining us today. My name is Alex Turenin. I'm a postdoc at the University of Cambridge and one of the organizers who will be hosting today. And I'd like to thank my fellow organizers, Jeff Pleitz, Lisa Simonova, and Zhe Wang, for the work in helping put the series together and bring all of our amazing speakers. And just before we begin, a few announcements. The first of those is that we've still got a few more speakers for this term lined up. So you can find the schedule for those on our website, which is gp-seminar-series.github.io. So check that out. You can join seminars via Zoom, provided you register to receive emails with the links, which can be done on the website, or you can join by watching via YouTube, which does not require registration. Seminars take place at 1600 UTC. So if you're joining on Zoom, you can use the raise your hand option to ask questions or type them in the chat. And the speaker can sort of pause to answer them during the talk, or they can take them at the end, depending on their preferences. And with this said, it is my pleasure to introduce Robin Rue, who is a PhD student at the University of Oxford, who will be giving today's talk, the topic of which is Bayesian optimization for neural architecture search. Robin, the floor is yours.
All right, thank you, Alex. And thanks everyone for coming for my talk today. And it's my great pleasure to go through this interesting topic of Bayesian optimization for neural architecture search with all of you today. So actually, in order to make my talk smoother, I think I will choose to turn off my video because I'm on my my internet is a bit unstable. So hello everyone, I'm Robin, and as Alex introduced, I did my PhD in Oxford, but actually I also did my undergrad and master in Oxford. So I'm a kind of full Oxford product. And during my PhD, I'm mainly supervised by Professor Michael Osborne, Stephen Roberts, as well as informally by supervisor Yaron Gao. So my main research interest focused on how to develop more efficient Bayesian optimization methods to tackling various AutoML challenges. But my broader interest also covers Gaussian process and Bayesian neural network. And recently, I've just finished my AI residency at Google X. So for today's talk, I'll first give a very brief introduction on Bayesian optimization as well as neural architecture search. And then I will go through two pieces of my recent work, focusing on how we can empower and enable efficient use of Bayesian optimization for the challenging task of neural architecture search. So without further ado, I will start by giving a very brief introduction on Bayesian optimization. So Bayesian optimization is a very powerful tool for black box optimization. It's particularly useful when the objective function that we want to optimize is a black box and it's very expensive to evaluate. So there are essentially kind of two key components in Bayesian optimization. The first component is that we need to define a statistical surrogate model to model the underlying unknown objective. And the Gaussian process is actually one of the most popular choice for Bayesian optimization. The second component is that we need to, based on the statistical model, define a utility function, which we call it as acquisition function. So the next point to evaluate or to search by the Bayesian optimization is actually proposed by maximizing the acquisition function. And the acquisition function itself is designed in such a way that it will automatically balance exploitation and exploration during the search. So essentially, Bayesian optimization transfers this very challenging problem of optimizing a black box unknown objective to a much simpler optimization task of optimizing this self-designed and often analytic acquisition function. So Bayesian optimization has been widely used for many applications. Besides the well-known use in hyperparameter optimization, it's also widely used in solving some industrial problems ranging from chip design to drug discovery and even material selection. As for the topic of neural architecture search, it's a really quickly arising topic in the AutoML field in the recent 2-3 years. So the idea of neural architecture search is to automate this manual process of designing the neural network architecture for any given tasks. And there are essentially 3 key components in neural architecture search. The first component is the search space design, which encompasses and comprise all the possible architectures that we can find in the search space. Based on that, then we will propose develop different search strategies to search within this big search space to find which architecture is the optimum for our task and objective. And finally, to evaluate, because the search is an iterative procedure, so we need to find a way to evaluate the performance of each search architecture. And the performance estimation strategy is actually the third most important part in your architecture search, in short, in NAS. So out of these 3 kind of building blocks, most of the research actually focused on the search strategy, the second component. And among various techniques proposed for the search strategy, Bayesian optimization is actually the most interesting one personally to me, and it's also my favorite option. So for today's talk, I will focus on how we can use Bayesian optimization for neural architecture search. So just to give you another, like a bit more background on neural architecture search on NAS, because there are so many kind of design choices for us to choose in the architecture search. The very popular kind of common convention in architecture search is actually not searching for the entire architecture directly, but rather searching for the repeating blocks in architecture, which we call it as cells. After finding the optimal structure of a cell, then we will stack them in a predefined way to kind of form the final architecture. And this significantly reduced the search complexity and the search dimension. And essentially, if we zoom in a little bit, we can see that each cell itself can be represented essentially as a directed acyclic graph with either operation or layer assigned to the node or to the edge of the graph. So in essence, actually, we can see directly here that neural architecture search can be naturally formulated as a task of finding the optimum labeled graph in the search space. And particularly, we need to not only finding the topology, which is defined by the adjacency matrix of the graph, but also we need to find what are the corresponding node features on each node. So to allow efficient search or effective search on this graph-like search space, the conventional practice is actually to propose some sort of encoding to encode this graph structure. So various types of encoding has been proposed, and they essentially encode not only the adjacency matrix and the topology, but also the categorical choices on each node into a long mixed type and vector. And this really make this problem of neural architecture search very high dimensional, and it's very difficult to optimize over because it involves a mixture of categorical and continuous variables. So despite the recent success in neural architecture search, actually there are many problems and challenges lying within this field. And for today's talk, I'll focus on these three major challenges, which are kind of addressed by two of our works, recent works, based on Bayesian Foundation. So the first kind of limitation of the current NAS method is that the NAS method is like any black box optimization task. It kind of lacks the interpretability in it. So essentially what it means is that after you specify the task and you spend lots of the searching power, it only returns you the final architecture without telling you other additional insights on why this architecture is good or why we choose that. The second problem is, as I described, such kind of a graph-like search space is very difficult to optimize. And finally, the use of cell-based design for the search space, while significantly reducing the search complexity for NAS, it also heavily limited the possible topologies for architecture search, leading to a search space that's seemingly large, but is actually not that expressive. So I'll go through each of these challenges in more detail as we proceed to talk more about the details of the work. So now, without further ado, let's jump into the first work, which we published in ICLR 2021, and we name it an interpretable NAS. So as I mentioned, the first challenge for the current NAS is that they all act like a black box. So we specify some sort of task and the objective. For example, we want to maximize test accuracy on Ceva 10, and then we run the NAS algorithm for many time and iterations. It returns spills out what's the optimal architecture to use. However, it didn't really give us much other insights about why this particular architecture is good or how the algorithm decide on to choosing it. So it can't really feed back those insights to manual design to help us guide and the future architecture design. So that's why we kind of propose this idea of interpretable NAS, hoping to open up this black box a bit more. And we want to essentially expanding the learning scope of NAS from purely returning a final architecture to also returning some human interpretable architecture sub-features, or we call it motives, that can really inform the user why those motives how those motives are contributing to the architecture performance. So it really this work marks this first step towards this direction of interpretable NAS. And besides this idea of interpretability, the second contribution of this work is that we actually propose a very query efficient BO-based NAS strategy, which we call it NASBO. And the gist of this strategy lies that leveraging the Wastphaler-Lehman graph kernel from the graph literature into the GP circuit, so that we can not only maintain the merits of Gaussian process in data efficiency, but also enabling the use of Gaussian process and the third BO to handle graph-like inputs naturally. So with this kind of a modification and our NAS strategy, BO-based NAS strategy and the GP circuit actually achieves very superior empirical performance, as I'll show later. So the key kind of component that contributing to the good performance of our BO-based NAS strategy is this Wastphaler-Lehman graph kernel. And I will quickly go through the main mechanism underlying it to give you some idea. So Wastphaler-Lehman graph kernel, WL kernel, is actually developed and inspired from the WL isomorphism test in comparing to kind of graphs. So without running any WL mechanism, now we can, well, if we want to compare this to architecture A and B, and at the initialization, the first kind of level of features we can extract are their corresponding node labels. So for example, the orange color indicates convolution 3x3 layer, and the yellow color indicates the convolution 1x1 layer, with green color indicates the input. So without running WL, we can extract those kind of node features to compare these two architectures. So now if we kind of kick off the WL mechanism, and the first step we did is to actually collect and aggregate the neighborhood labels for each node. So for the green node and for architecture A, we can see that it will collect its children node 1, 2, 2, 3 into itself. And then the next step we did is to recompress those aggregated labels into a new higher level feature. So for example, this green circle addition higher level feature 5 actually correspond to this subtree structure with a depth of 1. Then in the third step, we will relabel each node with their corresponding higher level features, and that completes one iteration of WL iteration mechanism. So as we can see that by running WL iteration, this actually leads us to extract higher level features. And essentially, as we kind of repeat this mechanism over and over, we will extract higher and higher level of features that correspond to a greater and greater neighborhood within the graph. So after doing that, then the WL kernel, graph kernel, essentially will compare these two original graph A and B based on the higher level features extracted, or the histogram of those higher level different features extracted at different level using the conventional basis kernel. So as we can see from previous case that depend on which level of WL iteration we are running, they actually extract different kind of sub-features or motifs. And those motifs corresponding to the earlier WL levels are actually quite interpretable to human users. For example, the h equal to 0, the initialization feature, are simply the node label or the operation types we assigned to each layer in the architecture graph. And the h equal to 1, the first WL level, actually correspond to this kind of a subtree feature, which in this case, like the sub-feature 6 is we observe this input connection to 3 3x3 layer and 1 kind of 1x1 layer. So it's something look like ResNext kind of structure. So now with those interpretable sub-features extracted, how can we make use of those motifs to explain the architecture performance? And the solution or the method, the technique that we adopt is to actually look at the gradient or derivative of the GP surrogate mean with respect to each of those interpretable motifs. So let's look at how it was done exactly. First, we kind of compute the local derivative of the expected derivative of our objective function with respect to each WL subfeature. And that kind of essentially equal to the gradient of the posterior mean, predicted mean of the GP surrogate with respect to each WL subfeature extracted. And this local gradient gives us some measurement of this local sensitivity of our final objective function, for example, test accuracy with respect to each features at a particular test graph GT. However, we then, that kind of only gives us some sort of local sensitivity. And what we are really interested in is actually the general sensitivity of the objective to each features, or in other words, how each interpretable subfeature contributing to the overall kind of architecture performance in general. And that's why we kind of marginalize over this local gradient over all the training architectures in the training set. and to obtain this average gradient. And this average gradient, which is kind of similar to the integrated gradient methods, gives us some local quantification, some quantification on the global or the overall sensitivity of the objective due to the presence of a certain interpretable motive. So in a nutshell, the interpretable WL subfeatures extracted by the WL mechanism in the graph kernel, together with this integrated gradient approach, gives us the final kind of interpretability in the NAS. And actually, in this case, we use integrated gradient for its convenience. And as we kind of get to learn more about explainable AI techniques, actually, we realize that you can use other options such as Shapley value or local approach like Lime to replace integrated gradient and to assess the contribution of those individual interpretable features. So now let's kind of validate, we also went on to validate whether this approach makes sense or give us some good performance. So we train our GP circle model on some training data, architecture data sampled from the search space. And then we kind of evaluate the average gradient as proposed in the previous slide on different motifs extracted by the WL mechanism. We then kind of label those motifs with the most positive average gradient as the best motifs, and those with the most negative average gradient as those worst motifs. So qualitatively, in this slide, we can see that the one particular motif, which is the best motif found by our approach and highlighted in the pink box, is actually, or a similar structure of it is present in not only the best cell found by our NAS strategy in the final experiments, but also it's present in the best architecture cells found by previous different NAS search strategies on the same search space. So as I highlighted in those pink shades, those kind of highlighted parts, they all correspond to this best motif identified by our approach. So this is kind of quite a reassuring qualitative results, showing that good motifs are actually present in different good architectures found by different search strategies. And quantitatively, we also went on to validate this further. So we train our surrogate model and kind of evaluate the motif quality as we proposed previously on 100 training data. And then we randomly sample 1,000 validation architecture from the search space, different search space. So here we actually validate on 3 NAS search space. Then instead of evaluating those architectures, we simply check whether we simply classify those validation architectures as good architectures if it contains at least one good motive, or we classify the architecture as bad if it contains at least one bad motive. And then we plot out the performance distribution in those plots, in each of the plot. So the blue color indicates the overall performance validation accuracy distribution for all the validation architectures. The red shades here indicates the performance distribution for those bad architectures classified by our simple approach. And the green color indicates the performance distribution of the good architectures we classified. So here on all 3 kind of search space, we can see that without evaluating those validation architectures, by simply checking whether there is presence of good or bad motives, we can already kind of separate those architectures, the good ones from the bad ones, to a decent extent. And moreover, we find out that those motifs are actually transferable across different data sets or different tasks. So for example, the motifs that we learn in this particular example, or those 3 plots I showed, we actually perform the motive learning only on the Cypher-10 task. And then we use the motives learned from Cypher-10 task to classify the architecture's performance on Cypher-100 and ImageNet tasks. So we can see that although the motives are learned on an old different task, it actually can be quite transferable to those new and different tasks. So that kind of gives us some hope that those motives are actually very transferable. And in fact, this also gives us, we also further demonstrate this, use a simple user case, transfer learning user case, whereby we perform or NASBO or BO-based NAS search on an old task, Cypher-10, and then we use the motives learned along the search to warm start or search on 2 new tasks, Cypher-100 and ImageNet. So specifically, we use the motives learned on the old task, Cypher-10, to help us prune and shrink the search space on the new tasks. So by doing this simple transfer learning of the motives learned, we can see that the results with transfer learning, which are in gray, actually leads to significant warm start or improvement over the cases whereby we search from scratch. So the red lines are the NAS kind of results when we search from scratch, and the gray line is when we're using this motive-based transfer learning to warm start the search. So we can see, especially at the start, the test error we found significantly dropped. So we can find good architectures right at the start by using motive transfer learning. So besides this interpretability kind of contribution, the surrogate model that we developed, which combines Gaussian process with WL graph kernel, actually itself is a very competitive surrogate. So here in this set of experiments, we compare or propose the surrogate, which are in red. We name it as GPWL, against a number of popular baselines in NAS. So we compared against the graph neural network in purple, and also we compared with a categorical kernel approach called combo in green. We also compared with an advanced encoding algorithm method proposed by White in 2019 in blue, as well as the original, one of the first BO NAS papers surrogate model called NASBOT in black. So here from across all the plots, across all the different NAS search spaces, we can see that our method in red significantly outperform all the other methods and requiring much less training data to achieve superior rank correlation. So the y-axis indicates the rank correlation. The higher means the better the surrogate model's prediction correlates with the true architecture ranking. And more importantly, and notably, our surrogate model is very scalable to high search space, so to larger search space. So as we move further and further to the right, the graph size or the architecture size in those search space actually gets bigger and bigger. And we can see that the advantage of this GPWL surrogate gets bigger and bigger over other competing surrogates on such kind of much larger search spaces. And the gain in the surrogate performance, regression performance, also translates well to the BO search performance when we incorporate that surrogate into our BO search framework. So on all these 8 plots, which correspond to different search spaces again, as well as on different search setting, we can see that our methods, which are in orange and the red, clearly outperform all the other competing methods in all the cases. And here, I'd like to just a quick note, which is for our method, we propose two variants following the practice in a previous work called bananas, whereby the subscript R indicates we use random sampling to optimize acquisition function, and M indicates we use mutation methods to optimize the acquisition function. Because of this graph-like search space nature for neural architecture search, actually optimizing acquisition function also becomes a bit challenging. So we cannot use gradient-based approach and need to resort to random sampling or genetic algorithm or this kind of mutation-based ones. So just one kind of quick note on possible extensions, which we find that in one of our recent NeuralRiffs paper, we find that this good combination of Gaussian process with WL graph kernel or WL feature extractor not only works for the neural architecture search tasks, but it also works on another kind of challenging graph-like search space, which is to perform adversarial attacks on graph classifiers. So in this case, we search perturbed graphs in the space to attack well-known graph classifiers. And we found that using BO methods that's based on WL graph kernel can really lead to clear improvement in the query efficiency compared to the existing SOTA methods. Now, okay, I'll move to the second kind of a work or second part of the talk, which is how we can reformulate the NAS problems to enabling us to achieve more efficient or favorable use of VO. And just a quick recap of the problems I highlighted earlier, that the second challenge, as we solved previously using graph kernel, is that the search space for architectures are graph-like. And if we do encoding, it will introduce this very high dimensional and mixed input type long vector, which makes the search very difficult. And potentially it will also lose the topology information. And the third problem is that while searching within a cell allowed us to significantly simplify the problem, it also limits the potential topology an architecture can take. And actually in the 2020 work by Yang, they found out the architectures sampled from the cell-based search space are not only very kind of close in their performance, but also very close in their topology. So if we look at this illustrative example highlighted here, these three architectures, A, B, C, they look very similar in their topology, and in fact, they have very similar test accuracy. So to conventional neural architecture search techniques, these three architectures, they appear as three kind of independent individual architectures and need to be evaluated repeatedly, one for each time, for each architecture. However, this kind of repeated evaluation on those highly similar architectures are really wasteful. So this motivates us to really think about whether we can group those highly similar architectures together into one family so that we can only spend one evaluation to evaluate one sample from this distribution family to estimate the overall performance of this entire distribution of architectures. This will allow us to significantly reduce the amount of repeated efforts in evaluating highly similar architectures and to really spend and reserve the evaluation power and the resource to evaluate those truly different architectures, which are likely coming from different generative distribution. So that's why in this particular paper, we kind of reformulate NAS as optimizing the distribution of architectures instead of a single architecture. To achieve that, we propose this graph-based hierarchical search space. And this search space comprises of 3 levels, whereby at the top level, it corresponds to the final architecture. However, each node in the top level in fact, correspond to a graph in the middle level, and each node in the middle level graph correspond to a graph at the bottom level. And each node on the bottom level correspond to one of the operation units we see conventionally in neural architectures. So this hierarchical kind of design really allowed us to achieve highly expressive topology structures for architectures. And as I'll show later, it allows us to generate a large variety of possible architectures from this hierarchical search space. On the other hand, to really kind of keep this search space tractable, instead of defining those topology connections at each hierarchical graph, at each level of graph, using a long list of categorical variables, we control the topology at each level of graph using a random graph generator. So here, essentially, we only need these 3 random graph generator to generate random topologies or random distribution of topologies for each at each hierarchical level. And the nice thing about those random graph generator is that they are only controlled or defined by a very small number of hyperparameters. So this really allows us, this combination, nice combination, really allows us to define a highly expressive search space with only a handful of continuous and categorical variables. In this case, it's below 10 of them. And this makes the search space much smaller and much amenable or favorable to the use of Bayesian optimization. So here are just some plots illustrating what's those random graph generator look like. And to give you an idea about the expressiveness of the search space, here I kind of randomly sampled some potential architectures from the search space by controlling the hyperparameter of the 3 graph generator. And we can see that the architecture structure can really vary from those very slim and sparse structure to those more densely connected ones. And in fact, we actually sampled architectures and evaluate them in the search space and evaluate different objectives, multiple objectives, such as the memory consumption, training time on these 2 x-axis, as well as the test error on the y-axis. And we observe that this search space gives us a large variety, covers architectures that have a large range of variety in multiple objectives. And this really motivates us to apply multi-objective BO search in this search space. So due to time constraint, I'll quickly go through those results, which simply shows that, oh, okay. I think I'm at actually slides 30. Okay. Can you
So
may I
we
ask
currently
which slide
see
are you
slide
at?
30 on the bottom right corner.
Okay, 30. Okay.
On the bottom right corner. You can try to unshare and reshare if you think that it's stuck.
Yeah, that's a good idea. So apologize for that. Does this resolve the issue?
We're still waiting for them to appear.
Oh, okay. Are you at slide 31 now?
It says has started screen sharing, but nothing has appeared, at least on my screen.
Okay.
One possibility would be to reconnect, but we still can hear your audio.
Okay, let me try and reconnect very quickly. Sorry about that. Yeah. And can you see my slide at 31 now?
Yes, that appears to now be working.
Okay, awesome. Apologize for that. Yeah, so this 31 illustrates the hierarchical search space I was describing, whereby we have these three hierarchies, and the node at higher hierarchy correspond to a graph at the bottom, at a lower hierarchical level. And instead of defining those topologies using a long list of categorical variables, we control the topology at different hierarchy levels using random graph generators or random graph models. And the nice thing about those random graph models is that they only involve a very small number of hyperparameters to be defined. So essentially, we obtain this highly expressive search space by defining only like a handful of below 10 categorical and continuous integer and continuous hyperparameters. All right, so this gives you some illustration about how those random graph models generate different types of graph. And in this particular slide 34, I kind of generate some sample architectures from this hierarchical space to show that actually the space by controlling those a small amount of hyperparameters, we can really generate a large variety of architectures with a varying kind of a very broad spectrum of topology connections. So quantitatively, we again kind of sampled many architectures from space, and we found that the architecture, this hierarchical space can generate architectures that gives us a wide coverage of multiple objectives. So here in this case particular, like for example, figure A on Cepha 10, the x-axis shows the architecture's performance on memory consumption and the training time. The y-axis illustrates their performance on test error. And this really motivates us to perform multi-objective search in this expressive search space. And we do apply multi-objective BO technique, which leads to really good performance, as we show and qualitatively show in the red kind of Pareto front covered by the red dots. So finally, kind of we're comparing the use of BO on this hierarchical or hierarchical search space, and we find that it can lead to really good architecture performance, found really good architectures on different kind of image tasks. And more interestingly, here is something that I like to really highlight, is that if you look at this dashed black line on the diagonal, it actually represents the performance of random sampling in the corresponding search space. So different color correspond to different NAS paper or NAS strategy, and some of them are actually defined on very different search spaces. So here, very surprisingly, you can see that for some of the NAS methods, even after doing those fancy search strategy using RL or evolutionary algorithm, they actually lead to architecture's performance that's below the average of simply random sample from the search space. So this gives you like two key points, which is for those small cell-based search space, actually the architecture performance, the variation of architecture performance of random architectures performance is pretty small, and which makes those fancy or advanced search technique not necessary or leads to very marginal gain. Whereby in our case, in our hierarchical search space, in combination with BO, we observe the biggest gap between the final search architecture performance over random sampling. So this really tells us that our search space is really expressive, and the use of advanced search strategy like Bayesian Foundation really makes a big difference. So this is the final summary slides, whereby we kind of recap the three kind of main challenges described throughout the talk. and how we kind of address them using these two approach, Nagel and NASPO. Particularly, the Nagel proposed a hierarchical graph-based search space, which is expressive in its nature, but with this distributional reformulation, the search dimension is very low. So it's very friendly for Bayesian Foundation. And for the NASPO, it uses the WL graph kernel to handle graph nature of the architectures. And it leads to really query efficient surrogate and also good optimization performance. And meanwhile, it also returns interpretable insights on top of the final searched architecture. So the third component, performance estimation, I didn't have time to cover it now in today's talk, but actually this is also one of the pain points of neural architecture search, because this is usually the computational bottleneck within a neural architecture search task. And recently in two of my work, actually I focus on proposing very efficient and cheap performance estimation methods to really reduce the search cost, so that we can allow BO to be on par with some other gradient-based or weight sharing techniques in your architecture search. So with that, I'd like to conclude my today's talk, and thanks for your attention and your patience with my poor internet.
So thank you very much for the talk. We will now move to the question, answer, and discussion period. And so the format for this is that we will have a brief period of questions that will be live streamed, and following that we will conclude the live stream for those that prefer not to be recorded and continue the discussion on Zoom. And for now, you can use the chat or raise your hand feature to ask your question, and we will unmute you to let you speak. And I already see that Jeff has a question, so I will click that.
Yeah. Hi, Binxin, thanks so much for the super interesting talk. I had a question about the gradient estimation. So I think this seems like it's going to be very highly dependent on your exact choice of Gaussian process surrogate model, because I feel like, just thinking about in terms of like other, doing other sort of derivative estimates with Gaussian processes, it's, if in sort of like for Gaussian processes with standard kernels, like using an RBF kernel versus using a Maturin kernel is going to give you very different properties of your derivatives, due to the smoothness assumptions encoded. And so I guess, can you describe how your specific choice of kernel is affecting these derivatives, and whether or not you saw that there was a significant amount of variability in those derivative estimates when you did any sort of hyperparameter searches?
That's right. All right. Thank you for your question. So actually, in our particular experiment, we played with the RBF, the conventional RBF kernel, and also we played with the linear kernel, and we found that and they do lead to some difference, but after doing the marginalization, they almost kind of reach very similar conclusions. And the nice thing about this WL graph kernel, and if we go back to this illustration slides, is that after it does the WL mechanism and extracts those feature, different levels of features, latent space, we can apply any type of conventional kernel on top of it. And in our case, we optimize the kernel hyperparameter using marginal likelihood, and we optimize how many WL iteration we want to run this hyperparameter H, together with all the other kernel hyperparameters as well. Yes. Hope that answers your question. So one small note is, initially, we kind of start off actually with this local estimation of the gradient, but we found it's actually, initially we were thinking of using that to guide the mutation of those architectures to help the search. But we found the gradients estimated locally tend to be really noisy. and it didn't give us very informative insights. So that's why after we kind of go back to do this global gradient estimation, and it gives us more consistent results. Yep.
I see. Thank you.
Hope that answers your question. Yep.
Yeah, that does. Thank you.
All right. And any other questions? I think Ziwang has a question as well.
Hi, Robin.
Hi.
Can you hear me? Okay, cool. So yeah, thank you for the really great talk. And actually also have a question on this particular slide. This derivative of objective or each feature almost reminds me of like some techniques in neural network compression, where they sort of like look at the contributions of each neuron and then take away those that doesn't contribute that much to the eventual output. I think that's roughly how it is. So I wonder like whether that has any connection to these values here, because I know these are actually neural network. I mean, like Gaussian process, mean function, and like marginalizing over those particular features. Yeah, just wondering like what kind of relation there might be.
All right. Yeah, thank you for your question. So, yeah, exactly. So for the neural network pruning, actually, people use these saliency maps. They call it saliency maps, which is essentially the gradient or the magnitude of the gradient with respect to each neuron to do the pruning. And in this actually integrated gradient methods for interpretability or explainable AI, the gradient is done with respect to the input features, and to help you select what are the most important input features. So I think the key difference here is first we use Gaussian process, which gives us this nice analytic gradient computation for most of the conventional kernels. And also it gives, and the second difference I think here is essentially, if you think about it, we can do, if we replace the Gaussian process here with a graph neural network per se, then we can do this gradient-based approach to identify those in those latent feature layer, what are the important latent features after the multiple kind of graph convolution layers. However, the main kind of problem here is those latent features extracted by neural network or graph neural network, they tend to be abstract, and it's not that human interpretable as the ones extracted by the WL mechanism. So for example, even if we find out what features are important in those latent space, it's a bit difficult for us to go back and explain what are the sub-patterns in the architecture that are contributing to the performance. Whereby in this case, I think it's a combination of the interpretable feature extracted by the WL mechanism, plus this integrated gradient approach allows these interpretable NAS insights. Yep, hope that answers your question. Yep. Thank you.
I actually have another follow-up question. Actually,
yeah, sure.
Maybe separate one, but I want to see if anyone else have questions first.
I think the end of that question is a good time to move to the non-recorded part. So
okay.
Feel free to ask the question, and then I will make the concluding announcements and conclude the live stream.
Okay, great.
Okay,
so
great.
my other question is on the motive. Yeah, so I was wondering if those motive weights are actually retrained on different tasks when you're doing transfer learning. Or is it like you take the learned architecture and their weights, for example, on Zephyr 10, and then directly put that motive directly into another architecture?
Yep. So that's actually referring to this transfer learning part, which is so essentially those motives, they are essentially like a substructure of, or like a sub pattern of a neural architecture, and the weights of the architecture and in the architecture search is often, we didn't consider the weights of those operations. So in different tasks, those weights will be retrained, but in neural architecture search, usually we assume that like after retraining the weights on a new task, what's a good structure remain to be a good structure. So that's why those motives, when we're doing the selection and the application, we just take the structure of the motive, the topology of the motive, or the connection pattern among those operation layers as it is, and to do the search. And although on different tasks, when we do the true evaluation, the weights of those operations will be retrained on the corresponding tasks.
Yeah, that makes sense. Thank you.
Yep. Thank you.
All right. So now I would like to move to the final part, which will conclude the YouTube live stream and allow the remaining listeners to ask any questions that they don't wish recorded. And before doing that, I just want to thank all of our listeners on YouTube for joining us today, and remind that we have another seminar coming up next week, which you can find on our website, which is again, gp-seminar-series.github.io. And so feel free to check that out.